Let's look at solving this numerical question. Claims on a particular type of insurance policy, they follow a compound Poisson process. Okay, so there is the number of claims which is following a normal a Poisson distribution, and the amount associated with each of the claims. Let's see what it is. Annual claim rate of zero point 0.2 per policy. So the lambda value is around zero point 0.2 per policy. Individual claim amounts are exponentially distributed with mean 100. So 1 by lambda, which was the mean, it is 100. Okay. So the expected value of the claims is 1 by lambda, which is equal to 100. So okay, let's differentiate these two lambdas. In addition, for a given claim, there is a probability of 30% that an extra claim handling expense of 30 is incurred. So expense of 30 and the probability is 30%. So there is a 30% chance that the expense is 30, 70% chance that the expense is 0. Okay, the insurer charges an annual premium of 35 per policy. Use a normal approximate to estimate how many policies the insurer must sell so that the insurer has a 95% probability of making a profit on the portfolio in the year. Okay, so if he has to have a profit, then probably it is like the probability that the expenses total, the total expenses greater than, now that we are saying is charging 35 as a premium per policy, assuming that he is selling n policies, the probability that the total expenses is greater than 35n, it should be less than 5%. This is what I really want to find out. So which means I need to first find out the total expenses, the expected total expenses, or even the distribution first of all. So first let's expect the expected total expense. And we know there are two components of this expense. One is the expected claim. I could write it as expected value of X as well. So the expected claim amount plus expected expense amount. Now what is the expected claim amount here? We have seen that it is exponentially distributed with a mean of 100. So this is the expected claim amount. Then what about expected expense? This is it. There is a 30% chance that the expense is 30, 70% chance that the expense is 0. So 30% of 30, which is 9. So expected total claim is around 109 per policy. So because I am talking of n policies, so the expected total claim per n policies is 109n. Okay. Similarly, I should compute now the variance because we are using a normal approximation. So the normal approximation is talking about the normally distributed claims. The mean of them is 109n, and okay, 109n is the claim. So here we are talking about the policies arriving at a rate of 0.2. So typically I should multiply this 109n times 0.2. This is the mean of the total number, expected value of the total number of claims. So probably this is coming out as 21.8n. So this is right, because this is expected claim per policy, and if I have to multiply it with number of policies, it is 0.2 times n. So that's the reason I am getting 21.8. Okay, let me get into the variance as well. Now, if I have to look at the variance of the total claim, right, it is nothing but R. Yeah, variance of the total claim, if I have to get, I should look at it like the variance of, right, if I want to look at the variance of the total claim, I am looking at the variance of the claim amount plus the expense amount. Now, this is nothing but, or I could directly find out expected value of t squared. So that expected value of t squared minus expected value of, so variance of t I will be getting as variance of c, or I could very well write variance of t is nothing but expected value of t squared minus expected value of t whole squared. Right? Let's try that out. Expected value of t squared minus expected value of t whole squared. So if I have to find out expected value of t squared, it is nothing but expected value of e plus expected value of c whole squared, right, t squared. So I could very well write it as expected value of expenses squared plus expected value of claim squared plus 2 times expected value of claims times expected value of expenses. Now, expected value of expenses squared, if I have to talk of, what is the expected value of expenses squared? Yeah, expected value of expenses. So there is a 30% chance of 30 and there is a 70% chance of 0. So I can very well find out the expected value of the expenses squared, 0.3 times 30 squared. So this is 900 times 0.3, so this is 270. Now expected value of claims squared. What is, so we know that in case of claims, mean is 1 by lambda, which is 100. So the variance of an exponential distribution is 1 by lambda squared. So the square of this becomes 10,000. So variance of this is 10,000. So expected value of c squared minus expected value of c whole squared. This is equal to the variance 10,000. So expected value of c squared will become 10,000 plus expected value of c whole squared, which is again 100 squared. So this is becoming 20,000 plus 2 times expected value of c is 100 and expected value of e is 9. So this is coming out as 20,000 plus this is 1800 plus 270. So expected value of t squared is coming out to 22,070. This is expected value of t squared. And out of this, now I can find out the variance of t, which is nothing but expected value of t squared minus expected value of t whole squared. So which will work out to expected value of t squared is 22,070 minus expected value of t, which we have got earlier, 109 square. So this will give me the variance of t, right, if we try to find out. So variance of t comes out as 22,070 minus 109 square. So variance of T is coming out to this much. Now, yes, now we have got the expected value of T for one policy, and similarly now if the variance of T is also for one policy. Now again I can talk about for 0.2 n kind of policies, the variance is 0.2 n times this much. Right, the variance of n is 0.2 times 0.2 n times this much. Right, so this is the variance of n policies. Now I could clearly see what should be the number of policies that needs to be sold. So basically it is like the probability of the normally distributed values of 21.8 n with a mean and a variance of 2037.8 n. Right, this is the variance. This probability of it being greater than 35n should be less than 5%. So I could very well make it as a standard normal distribution. The probability that this is greater than 35n minus 21.8n divided by square root of 2037.8n. They should be less than 5%. So basically I am more interested in what is this 13.2 n divided by, so I need to find out the square root of this number, which will give me 45.142. 45.142 square root of n. So I should be able to find out 13.2 divided by 45.142 giving me 0.2924 root n. So 0.2924 square root of n. Probability of n01 greater than 0.2924 square root of n should be less than 5%. So which means this particular number 0.2924 square root of n should be greater than 1.645, and solving for this I should get square root of n is greater than 1.645 divided by 0.2924, and n should be greater than the square of this particular number. So I can very well compute that as 1.645 divided by 0.2924, this entire thing squared. So around 31.65. So at least a minimum of 32 policies need to be sold to make sure that there is a 95% probability of making a profit in the year. So it's a straightforward question trying to compute the number of policies required based on the distribution that we are seeing above. Alright.